Welcome back to Mechanical Engineering Made Simple.
It's great to be back.
You know, when we usually sit down for these deep dives, we tend to pick a topic that feels, well, clean.
Yeah.
We talk about thermodynamics in a perfect system or the ideal efficiency of an engine cycle. It's all very safe. It's theoretical.
It's the engineering equivalent of a frictionless vacuum. It's a nice place to visit, but nobody actually lives there.
Exactly. And today we're leaving that safe space entirely. We're going to try and debug the actual physical world.
I like that. Debugging the physical world.
We've got a stack of sources today that are, frankly, a little anxiety-inducing because they tackle the most asked questions that engineers grapple with online and in the field when things are going wrong.
We're talking about the moment the theory stops working. We're looking at why parts break when the math says they shouldn't, why machines shake themselves to pieces,
Yeah.
and how the environment, the vacuum of space or just the heat of a factory floor conspires to ruin your beautiful design.
The mission for this deep dive is pretty simple. We want to understand the failure modes that aren't in the introductory textbooks. We aren't just reciting definitions.
No, not at all. We're looking at the specific high-stakes problems that keep engineers up at night.
Debugging the physical world is really the right phrase for it.
Right.
In software, if you have a bug, the screen freezes.
Right.
In mechanical engineering, if you have a bug, a shaft shears off at 3,000 RPM, or, a bolt snaps and a pressure vessel vents.
The feedback loop is a lot more visceral.
To say the least. So we have a massive agenda. We're going to start with stress concentrations, the silent killers. Then we'll look at the assembly phase, specifically why bolts fail in places you would never expect. After that, we've got a huge section on vibration and balancing, and then we'll wrap up with isolation systems and some manufacturing horrors.
It is effectively the full life cycle of a disaster, from the drawing board all the way to the scrap heap.
Okay, let's just jump right in. Part 1. The source material refers to this as the silent killer. We are talking about stress concentrations.
Or, as it's often, colloquially known in the field, the problem with holes.
This is a huge topic on engineering forums. The question always looks something like this. I did the math. My average stress was, say, 20,000 psi. My yield strength is 50,000 psi. I had a huge safety factor. Why did my parts snap in half?
It's a heartbreaking question, because the math wasn't wrong, it was just incomplete.
Incomplete how?
The engineer calculated the nominal stress. They assumed the load was spread out evenly across the entire cross-section, like spreading butter on toast, even smooth coverage.
But steel isn't toast.
No, it's not. You have to visualize stress not as a static number, but as a flow. Imagine a river flowing smoothly down a wide, straight channel. The water lines, the streamlines are all parallel. Everything is calm.
Okay, I can picture that.
Now, imagine you drop a giant boulder right in the middle of that river.
The water can't go through the boulder, it has to go around it.
Exactly. And to get around it, the water has to speed up. The streamlines get squashed together right at the edges of that boulder. You get turbulence. You get a massive increase in the local velocity.
And in our solid metal part, that boulder is just a hole we drilled.
That's it. If you drill a hole in a plate, the lines of stress cannot pass through the empty space. They have to divert. They crowd together right at the edge of the hole. That crowding is the stress concentration.
So even if your average stress across the whole part is low, the stress right at the tiny, tiny bit of material at the edge of the hole could be 3, 4, maybe 5 times higher.
Precisely. That multiplier is what we call KT, or the stress concentration factor. And failure almost always begins there. The crack starts down the hole, or at a sharp corner, because that's where the flow is most turbulent.
I want to drill down, pun intended, on a specific detail from the research about the infinite plate assumption. I feel like this is something we all get taught in school, and it turns out to be, well, a bit of a lie.
It is convenient fiction, for sure. In university, you learn that for a circular hole in a plate under tension, KT equals 3, period. Always 3. The peak stress is 3 times the average stress. You memorize it, you write it on the exam, and you move on.
But the sources are really clear that this formula only works if the plate is infinite. It assumes the edges of the plate are miles and miles away.
And have you ever designed a bracket that was infinite in size?
Can't say I have, no.
Right. In the real world, we design tight, compact parts. We put holes near edges to save weight and space. And the research shows that as your hole gets closer to the edge of the part, that magic number of 3 goes completely out the window.
Because there isn't enough material on the outside of the hole to handle that diverted flow of stress?
That's it, exactly. Go back to our river analogy. If you drop the boulder right next to the riverbank, the water is forced into this tiny high-pressure channel between the rock and the bank. The velocity just skyrockets. In metal, if that ligament, the little bit of material between the hole and the edge, is thin, the stress concentration can jump to 5, 6, or I've even seen it go to 10.
So if you're using KT equals 3 in your safety calculation, but your hole is close to an edge, you're effectively flying blind.
You're underestimating the peak stress by double or even triple.
Mhm.
And that is why parts fail when the average stress looked totally safe.
Okay, let's talk about the geometry of the hole itself. One of the papers we looked at had a fascinating comparison between a standard straight shank hole and a countersunk hole.
Ah, yes. This is the classic conflict between the industrial designer and the mechanical engineer.
Right, because we want the screw head to be flush. It looks clean, it's aerodynamic, we love our countersinks, but the finite element analysis data suggests we should probably hate them.
We should be very, very wary of them. When you countersink a hole, you're doing two things. First, you're obviously removing more material so you have less bulk to carry the load. But second, and this is more important, you're creating a complex three-dimensional geometry. The stress doesn't just flow around a simple circle anymore. It has to navigate a conical expansion.
And the data shows that the stress concentration is heavily dependent on the angle and the depth of that countersink.
It is. The sharp transition at the bottom of the countersink where it meets the straight hole acts like a notch. It creates a localized peak that is significantly higher than a straight hole. If you're designing something for a high-fatigue environment, something that vibrates or takes cyclic loads, a countersunk hole is a weak point you really need to justify.
It really sounds like if you can get away with using a button head or a socket head screw that sits on top of the surface, you should probably do it.
Structurally, yes. Almost always the better choice.
Speaking of sharp transitions, let's talk about grooves and notches. This feels like the cousin of the whole problem.
It is. A groove for a retaining ring or a relief for a thread is essentially a deliberate crack that we machine into the material.
And the math here, it all relies on the relationship between the radius of the notch, let's call it R, the diameter of the bar, and the depth of the cut.
The most critical variable in that entire equation is R, the radius. There's a fundamental rule in fracture mechanics. Sharp corners are the enemy.
Why is that, mathematically speaking? What's going on?
Because a perfectly sharp corner where the radius is 0 creates what we call a mathematical singularity. The equation for stress involves dividing by the radius. If that radius is 0, the stress is theoretically infinite.
Infinite stress, that sounds bad.
It's less than ideal, yeah. In reality, what happens is the material yields, it stretches plastically to blunt that sharp tip just a microscopic amount. But you're starting from a massive deficit. You're asking the material to save itself from a singularity every single time you load it.
Which is why we always hear about fillets, these rounded internal corners being so critical in design.
A fillet allows those stress streamlines to curve gently around the corner rather than crashing into a wall. It smooths the flow. It's a gentle turn instead of a 90-degree dead end.
But the source mentions a constraint here that I think every manufacturing engineer has run into. Sometimes you can't use a fillet.
Right. Manufacturing gets in the way. If you're drilling, the drill bit has a specific shape. If you're machining a shaft where a bearing needs to seat, that bearing has a sharp corner, so the shaft needs a sharp corner to match it.
So you're stuck. You need the sharp corner for the assembly to work, but the sharp corner is what's going to kill the part.
That's when you have to get clever. Use things like undercut grooves. You actually cut deeper into the shaft, but with a nice big round radius, so the stress flows smoothly through the empty space you've created. But the vertical wall is still there and flat for the bearing to sit against.
So you actually remove more material to make the part stronger.
Counterintuitive, isn't it?
Yeah.
But yes, by removing material in the right shape, you are guiding the stress away from the danger zone. It's about controlling the flow.
Before we leave stress completely, we have to talk about the crankshaft oil hole. This was a specific case study in the notes that really highlights how complex this all gets in the real world.
This is the absolute nightmare scenario for stress analysis.
So just to set the scene, picture a crankshaft in an engine. It's pushing pistons up and down, so it's bending, it's transmitting torque to the wheels, so it is twisting, and it is spinning at thousands of RPM.
It's under what we call a complex stress state. Bending plus torsion. It's one of the hardest things to analyze.
And then we decide to drill a hole right through the most highly stressed part of it to let oil in.
It feels wrong just saying it, doesn't it? You are taking the most highly stressed component in the entire vehicle and deliberately punching a hole in it.
But the analysis shows it's not just a static hole. Because the shaft is rotating, the stress field around it is rotating too.
That's the key. The location of the peak stress travels around the rim of that oil hole like the hand of a clock. It is constantly moving, constantly cycling.
The source points out that if you don't radius the edge of that oil hole perfectly, I mean, if you leave even the slightest sharp edge or a burr from drilling, the crankshaft will fail.
It is a guarantee. It's not just about the design on paper. It's about the execution. If the machinist gets lazy and doesn't polish that oil hole radius properly, the KT factor doubles and the engine blows up. It really proves that manufacturing quality is a structural variable.
That is a perfect transition to part 2. We've designed the parts, we've worried about all the holes, now we have to actually put them together. Let's talk about designing for assembly, specifically bolts, nuts, and press fits.
The humble bolt, the most common machine element in the world, and yet I would argue probably the most misunderstood.
I have to admit, I fell right into the trap here. The big question is, where is my bolted joint actually going to break? And I looked at a bolt and thought, okay, the shaft is the thinnest part. It'll break somewhere in the middle of the smooth shank.
That's what intuition tells you. It makes perfect sense.
Yeah.
But the statistics from the field tell a very, very different story.
Let's break down the data from the source because it's pretty shocking. It lists the failure locations. Only 15% of failures happen under the head of the bolt.
Usually because the fillet radius under the head was too tight, creating a stress concentration, a classic sharp corner problem.
Okay. Then 20% happen at the end of the thread, with the thread stop and the smooth shank begins.
Again, a geometry change, another stress riser.
But a massive 65% of failures happen inside the thread, specifically at the face of the nut.
That is the danger zone, 65%. 2 out of every 3 failures.
Why? Why is the nut face so lethal to the bolt? It's buried inside the nut. It should be protected.
It all comes back to the flow of forces. When you tighten a nut, you assume that all the threads are engaging perfectly. You imagine that if there are, say, 10 threads inside the nut, each one is carrying 10% of the load.
Right, like a team of 10 people pulling a rope. Everyone pulls their own weight.
That's the ideal. But in reality, the bolt is stretching under tension, and the nut is compressing under the load. And because of this deformation, the threads don't mesh evenly at all. The very first thread, the one right at the face of the nut, the one touching the washer, takes the vast majority of the load.
So the first person in the tug-of-war line is actually holding 80% of the weight, and the people at the back are just kind of standing there.
Exactly. The literature suggests the first thread can take up to a third of the entire load. The second thread takes a little less. By the time you get to the 5th or 6th thread, they're barely carrying any load at all. They're just along for the ride.
That creates a massive stress peak right at the root of that first thread.
And that is why it snaps there. It's a localized overload that the rest of the bolt never even feels.
So knowing that, how do we fix it? The source discusses something called a reduced shank bolt. And this brings us back to that weird theme of removing material to make something stronger.
Yes, it's a fantastic design.
Yeah.
A reduced shank bolt has the smooth middle section, the shank, turned down on a lathe so it's actually thinner than the threaded section.
Which sounds completely insane. You make the bolt thinner to make it stronger.
You make it more elastic. By thinning the shank, you lower its stiffness. It can stretch more under the same load.
Okay, so it's stretchier. I'm with you so far. But why does that help the thread?
Because that added elasticity in the long shank acts like a shock absorber. Instead of the force slamming directly into that first thread, the long, thin shank stretches and absorbs the strain energy. It allows the load to distribute more evenly across all the threads.
So a big, thick, stiff bolt is actually a bad thing because it forces the threads to do all the work.
Correct. In a fatigue situation, a stiff bolt is brittle. It transfers all the shock to its weakest point. A reduced shank bolt, a more flexible bolt, shares the burden along its entire length.
That is a fascinating insight. If you want fatigue life, you want flexibility, not just raw bolt.
Precisely. It's about strain distribution.
The source also mentions modifying the nut itself.
Yes, there are a few clever tricks. You could use buttress threads, which have an asymmetric shape designed to direct the force better. Or you can simply optimize the radius of the thread root in the nut.
Just making the little curve at the bottom of the V-groove bigger.
That's it. The data shows that just by changing the curvature at the bottom of the nut thread, you can reduce the peak stress in the bolt by as much as 22%. That is free strength. You don't add material, you don't change the material grade, you just change the shape of the curve.
Okay, let's switch gears from bolts to press fits. This is when we don't use fasteners at all. We just force a pin into a slightly smaller hole and rely on friction.
It is the standard way to mount gears, bearings, and pulleys onto shafts. Simple, cheap, effective. But it has a dark side, a really dark side, called fretting corrosion.
Fretting corrosion. It sounds like something that happens to an old car left out in the rain, but this is happening inside a brand new, super tight joint.
It is. Fretting is damage that's caused by microscopic motion. Even though a press fit feels rock solid under heavy vibration or cyclic loading, the two parts might slip against each other by just a few micrometers.
Just a tiny little bit of rubbing.
Tiny rubbing, back and forth, millions and millions of times. And that rubbing scrapes off the oxide layer, the protective skin of the metal. It creates this fine red dust. The source calls it oxide dust, but engineers sometimes call it cocoa.
And because the joint is so tight, that dust has nowhere to go. It can't get out.
Right. It stays trapped in the joint and acts like an abrasive. It's basically sandpaper. It grinds away the surface, creates tiny pits, and eventually those pits become the starting point for fatigue cracks.
So a press fit isn't just a static hold. It's a chemically active, grinding environment if you have any vibration at all.
Exactly. The joint is alive, and it's trying to eat itself.
Speaking of things that are alive and shaking, let's move on to part 3. Things that spin. Vibration, balancing, and bearings.
The dynamic world. This is where the static math we all learned really starts to fall apart.
The big question engineers are always asking here is, why is my rotating equipment vibrating? And I think the rookie answer, the first thing everyone says is, it's unbalanced. Just stick a weight on it.
Heavy spot on the left, put a weight on the right. That is static unbalance. And honestly, it's the easiest thing in the world to fix. But the sources we're looking at today describe a whole gallery of other culprits that are much, much harder to spot.
Let's run through a few of these because they are really sneaky. First one on the list, dissymmetry.
This is a classic manufacturing defect, usually in castings. Imagine you're casting a hollow steel rotor. You have an outer mold and an inner core. If that inner core shifts by just a millimeter during the pour.
The wall thickness will be uneven. One side will be thicker than the other.
Exactly. But the outside is then machined perfectly round. You can measure it with a micrometer and it's dead on. But because one wall is thicker, the center of mass is offset from the geometric center. You have a heavy side that is built into the very geometry of the metal.
Okay, then there's non-homogeneous material.
Blowholes. Slag inclusions. Imagine you have a beautiful, solid steel shaft, but deep inside, there's an air pocket the size of a grape from the casting process.
That air pocket has no mass.
So your center of gravity shifts away from the hole. Again, you cannot see it, you cannot measure it from the surface. You only find out it's there when you spin the machine up to 5,000 RPM and the whole floor starts shaking.
Here's one that I found really unsettling. Distortion at speed.
Ah, yes.
Yeah.
This is the unbalance that only exists when the machine is actually running. The fandom.
The source used the example of blower blades on a large fan.
Right, so you balance a fan in the shop at low speed. It's perfect. You install it, you turn it on, it vibrates. Why? Because at speed, centrifugal force is pulling on those blades with thousands of pounds of force. If one blade is slightly weaker, maybe the metal is a tiny bit softer, it stretches more than the others.
So the actual shape of the fan changes while it's running.
It deforms, elastically or sometimes even plastically. The center of mass moves outward on that one blade. The unbalance is created by the rotation itself.
And when you turn it off, it shrinks back and it looks perfect again. It's a ghost in the machine.
It is extremely frustrating to diagnose. You're chasing something that isn't there when you're looking for it.
And then there's a big one for heavy industry, thermal gradients. The paper mill roll example was perfect.
This is a classic. You have a long, hollow steel roller that's heated internally with steam. If the heat isn't applied perfectly evenly, if the bottom gets hotter than the top, the metal expands more on the hot side. The roll bows. It physically turns into a banana.
And trying to spin a heavy steel banana at high speed is noticeable.
It generates massive forces. And the tricky part is that the vibration fluctuates. It might run smooth in the morning when the machine is cool, and then by the afternoon, when it's fully heat-soaked, it's shaking the entire building down.
Now, when a machine vibrates, the first thing that usually gives up and breaks is the bearing.
The bearing is the victim. It is almost always the victim, takes all the abuse.
The source has a very strict warning here that I think is so important. Don't assume a failed bearing means you need a stronger bearing.
This is the #1 mistake in maintenance. An engineer sees a broken bearing and thinks, okay, I need a higher load rating. I'll buy the super heavy-duty version.
But if the root problem is that the shaft is bending like a banana from heat, a stronger bearing won't help one bit.
It will just transfer those massive forces to the housing.
Hmm.
Or it will fail just as fast. You are treating the symptom, not the disease. You're putting a stronger fuse in a circuit that's shorted out.
Let's look at some of these root causes that kill bearings. The source lists cross-location.
This is a really common assembly error. You have a long shaft that's held by two bearings, one on each end, and you lock both of those bearings down tight to the frame so they can't move.
Okay, sounds secure.
Now, the shaft heats up from operation. Metal expands when it's hot, it gets longer. But the bearings are locked. The shaft has nowhere to go, so it pushes outward, effectively trying to push the bearings out of their housings.
You are crushing the bearings from the inside out.
You're loading them with thousands and thousands of pounds of axial force just from thermal expansion. The proper design is to have one floating bearing that can slide a little bit to accommodate that growth.
Okay, here's a term I hadn't heard before. False Brinelling. I know Brinelling is when you dent the race of the bearing from a heavy impact, but what makes it false?
Real Brinelling is from a heavy hit, like dropping the shaft. False Brinelling happens when the bearing isn't moving at all.
Wait, how do you wear out a bearing that is standing completely still?
Passive vibration. Imagine you have a backup motor sitting on a factory floor. It's turned off. But the floor is vibrating because there's a giant press damping parts nearby.
Right.
The balls in that stationary bearing are jiggling against the race in the exact same spot, tap, tap, tapping millions and millions of times a month.
It digs a little divot.
It wears a perfect little depression into the hardened steel.
Ah.
Then 6 months later, there's an emergency, and you finally turn that backup motor on. It sounds like a bag of rocks.
It broke without ever having run. That is insidious.
It happens constantly in transport, too. Shipping cars on a real car can ruin the wheel bearings from the vibration of the train before the car is ever even sold.
We have to talk about the scariest category of vibration before we move on. Self-excited vibration.
The instabilities. This is where things get really weird.
The source is careful to distinguish this from forced vibration. Forced vibration is like the heavy spot. If you remove the weight, the shaking stops. The effect is proportional to the cause.
Right. But self-excited vibration is totally different. It is a feedback loop. It feeds on the motion itself.
The source lists some terrifying names like oil whirl and fluid bearing whip.
Oil whirl is fascinating. Inside a fluid film bearing, the shaft is supposed to ride on a stable wedge of pressurized oil. But under certain conditions, usually light load and very high speed, the oil film itself starts to swirl around inside the bearing clearance.
Like a mini tornado of oil inside the bearing.
Exactly. And that swirling oil pushes the shaft. The shaft moves, which excites the oil film even more, which makes it push harder. The vibration creates the force that causes the vibration.
It's a runaway train. The more it shakes, the more it wants to shake.
It is. And the terrifying part is you can't balance your way out of it. You can balance that shaft to zero, make it mathematically perfect, and it will still whirl because the problem is in the fluid dynamics, not the mass distribution.
So we've got stress, we've got bad assembly, we've got ghosts in the machine causing all this vibration. At some point, we just have to accept that the machine is going to shake and we have to isolate it. So part 4, controlling the shake.
The art of decoupling, how to break the connection.
The big question here is obviously, how do I isolate this machine from the floor? Or, just as important, how do I protect the sensitive equipment on the floor from the machine?
We have a whole menu of options here. We can start with the most common one, elastomers. Rubber and plastics.
Rubber seems simple, but the source dives into something called the bulging rule, which I found fascinating.
This is critical to understanding how rubber works. Rubber is viscoelastic, but more importantly, for practical purposes, rubber is effectively incompressible. You cannot change its volume.
So if I squeeze a rubber block, the material has to go somewhere else.
Think of a rubber eraser. Put it flat on your desk and press down on it hard with your thumb. It gets shorter, but it also gets fatter. The sides bulge out.
Right.
That bulging is the only reason it feels soft. It's the only way it can compress. If you were to put that same eraser inside a tight steel tube so the sides couldn't bulge and that you tried to press down, it wouldn't move. It would feel as stiff as a block of steel.
So the stiffness of a rubber mount depends entirely on its geometry and how much room it has to bulge.
Completely. When you design a rubber isolator, you have to give the rubber room to expand sideways. If you confine it, you lose all the isolation.
The source also warns about bonded versus unbonded isolators. What's the difference?
An unbonded isolator is just a simple rubber pad that you set between the machine and the floor. Friction is what keeps it in place.
Okay, but what happens if oil or water gets underneath that pad?
You lose the friction. The rubber starts to slip sideways. It bulges too much. The source notes that the stiffness can drop by 50% or more just because the interface got wet or oily.
So your machine suddenly starts bouncing around wildly because the floor got slippery.
Exactly. The characteristics of your system completely change. That's why bonded isolators, where the rubber is chemically vulcanized directly to the metal plates, are much safer and more predictable.
Okay, let's move from rubber to metal springs, like helical coils.
Metal springs are great for low frequencies. If you have a heavy machine that's shaking slowly, steel springs are fantastic. But they have a huge weakness, damping.
Or complete lack thereof.
Steel has almost no internal damping. So if you happen to hit the resonant frequency, the natural hum of the spring, it will amplify the vibration. The source says the transmissibility can be greater than 100.
That means it actually makes the shaking 100 times worse.
Yes, it can be absolutely catastrophic. Also, high-frequency noise travels right through steel wire like it's not even there. If your machine makes a high-pitched buzzing sound, a steel spring will transmit that buzz directly to the floor and turn the floor into a speaker.
So you often see a rubber pad under the steel spring to catch those high frequencies.
A hybrid approach is often the best solution. Yeah.
Then we have Belleville springs. These are the coned discs, the stacked washers.
They look like Pringles made of steel. You stack them up. They can handle immense loads in a very, very small space.
And there's a mathematical sweet spot here that the source points out regarding the ratio of the cone's height to the material's thickness.
Yes. If you make the ratio of the cone height, E, to the thickness, T, about 1.5, you create a constant load spring.
What does that mean in practical terms, a constant load spring?
It means you can compress the spring a little bit, or you can compress it a lot, and it pushes back with the exact same force at a flat rate. This is incredibly useful for things like clamping gaskets or seals, where parts might shift or expand with temperature, but you need the clamping pressure to stay exactly the same.
All right, let's talk about the Cadillac of isolators, air springs.
Air is an amazing spring. It stores more energy per pound than steel or rubber. It's incredibly efficient and adjustable.
But the physics here got really deep. The source started talking about thermodynamics, specifically adiabatic versus isothermal compression. Can we break that down?
Sure. It sounds complex, but it really just boils down to heat. When you compress a gas, it gets hot. We all know this from using a bicycle once.
That makes sense.
If you compress that gas very, very fast, like in a high-frequency vibration, the heat doesn't have time to escape the gas. It gets trapped inside. That is called adiabatic compression.
And hot gas is stiffer. It pushes back harder.
Yes. The pressure rises much faster. The adiabatic index for air is 1.4. So at high frequencies, an air spring is actually quite stiff.
But what if the vibration is very slow?
If it's very slow, the source says less than about 3 hertz, the heat has time to flow out of the gas and into the walls of the airbag, which then radiate it away. That is isothermal compression. The gas stays cool.
And cool gas is softer.
Much softer. The index drops to 1.s. So uniquely, the stiffness of an air spring changes depending on how fast you shake it. It's soft for slow, big motions and stiff for fast, small motions.
That is wild. The spring rate is literally a variable that depends on the input.
It is. And there's a cheat code mentioned in the source that I absolutely love, using sulfur hexafluoride gas instead of regular air.
SF6. I've heard of it for electrical switchgear.
It's a very heavy, dense gas. The molecules are huge and lumbering.
Why on earth would you fill a spring with that?
2 really clever reasons. 1, the molecules are so big that they don't leak out through the pores in the rubber nearly as fast as nitrogen or oxygen do. It holds its pressure better. But 2, the thermodynamics of SF6 are different. Using it reduces the stiffness of the spring by 22% compared to using air.
So if you need an ultra-soft isolation system, say for an electron microscope or delicate optics table, you just swap the gas.
Exactly. It's a chemistry hack for a mechanical engineering problem. It's brilliant.
Okay, part 5. The environment and life cycle analysis. This is about stepping back and looking at the bigger picture.
Yeah, the context in which the machine actually lives and works.
The big question here is, will this thing I designed survive the actual operating environment? And the source makes a point that I think is profound. The life of the equipment begins at manufacture.
We tend to think a part is fresh when we take it out of the box, 0 miles on the clock. But if that part was welded, it has massive residual stresses locked inside from the heating and cooling process. If it was machined aggressively, the surface is stressed. The part is already tired before you even turn it on for the first time.
It's carrying baggage from the factory.
Exactly. And if your stress calculations don't account for that residual stress, you are eating into your safety margin from day one.
Let's talk about some extreme environments. First up, vacuum.
Space, or high vacuum manufacturing chambers for semiconductors.
Two big things happen here. First, no air means no air damping.
Right. Here on Earth, air resistance is constantly helping to stop things from vibrating. It's a natural cushion. In a vacuum, if you flick a tuning fork, it rings for a very, very long time. You lose that free energy dissipation.
And second, and maybe more dramatically, pressure differentials.
If you build a sealed box full of air on Earth and then you send it to space, that box instantly becomes a pressure vessel. The air inside is pushing out with 14.7 psi against the perfect vacuum of space.
It wants to explode.
It balloons.
Yeah.
That creates a huge amount of stress in the casing before the machine inside even starts working. You have to vent everything or you have to build it like a submarine.
And let's quickly touch on thermal realities.
Heat transfer. It's never as simple as the textbooks say. The source talks about thermal spreading resistance. Imagine a tiny little computer chip that's generating a ton of heat, and it's attached to a big aluminum heatsink.
Okay. The heat has to flow from the small area of the chip to the big area of the heatsink.
And there's a resistance there, a bottleneck, just due to the geometry. The heat can't spread out instantly, so it backs up at the source.
And what about contact resistance?
This brings us right back to the microscopic scale. You press two perfectly flat, polished pieces of metal together. To your eye, they are touching perfectly everywhere. But under a microscope, it looks like two mountain ranges just touching at their highest peaks.
So the actual contact area is just a tiny fraction of the surface.
It can be less than 5% of the total surface area. All the heat has to try and squeeze through those tiny little contact points. The rest is air gaps. That's why we use thermal paste to fill in all the valleys and create a continuous path for the heat.
Okay, finally, part 6. This one is for the people on the factory floor, the tools themselves. Why is my tooling failing during production?
This is for the manufacturing engineers who actually have to make all this stuff we design.
The source lists some incredibly specific faults. I love this one. Chip hammering.
It sounds like a heavy metal band, doesn't it?
It really does. But what is it mechanically?
It's when the metal chips you're cutting off apart don't fly away cleanly. Instead, they curl back around and they smack the cutting edge of the tool that just made them.
So you are cutting metal, and the debris from the cut is beating up your tool.
It is literally hammering the brittle ceramic or carbide insert. It shatters the tool life. The fix is to change the feed rate or the geometry of the tool to make the chips form a different shape and fly somewhere else.
And thermal cracks. The source gives the advice that I love. Don't dribble.
This is all about applying coolant. Carbide tools absolutely hate thermal shock.
So if you just splash a little bit of coolant on them intermittently?
They get red hot when they're cutting, then a splash of cool water shocks them, then they get hot again. They crack like a hot glass you put in a sink full of cold water.
So what's the rule?
Flood it. Drown the tool in coolant so it never gets hot in the first place. Or turn the coolant off completely and let it run hot and steady. But don't tease it. No dribbling.
And lastly, heat treatment failures.
This is where you can ruin a perfectly good part in the very final step of the process.
The main culprit is listed as drastic section changes.
If you have a tool with a thick, heavy handle and a thin, delicate blade, and you heat it up cherry red and then dunk it in water to quench it,
The thin part cools instantly.
and the thick part stays hot for much longer. The thin part shrinks and hardens while the thick part is still expanded. The internal war between the two sections pulls the metal apart. Bing! You hear a little noise and you've got a crack.
And the fix.
Use an air-hardening steel which cools much more gently. Or, once again, use fillets. Smooth out the transition between the thick and thin sections so the heat can flow more evenly and the stresses aren't so concentrated.
It really all comes full circle, doesn't
Yeah.
it? Whether it's the KT of a tiny hole in a crankshaft, the radius of a bolt shank, or the cooling of a complex tool, it is all about geometry and flow.
It is. We started by saying we wanted to debug the physical world. And I think the big lesson from all these sources is that the physical world is fundamentally hostile. It relies on entropy. It wants to fatigue your part. It wants to corrode your press fit, and it wants to shake your bearings to dust.
And our job as engineers is to anticipate that hostility, to outsmart the stress concentration, to give the rubber enough room to bulge, to float the bearing.
Exactly. The design on paper is just the starting line. The real finish line is a part that survives the absolute chaos of reality for its entire design life.
Well said. And here is a final thought for you to mull over. We talked about using SF6 gas to passively change the stiffness of an air spring. It makes you wonder, as we move into an age of smart materials and AI control, could we design structures that change their own gas composition or stiffness in real time?
Adaptive structural tuning. So if a bridge starts to vibrate in the wind, it senses the frequency and actively changes its own stiffness so it's no longer at resonance. You just dodged the bullet. I like that
Yeah,
a lot.
something to think about.
Mm.
All right, that's a wrap for this deep dive.
It has been a pleasure.
If you haven't already, get over to our YouTube channel, Mechanical Engineering Made Simple, where we post hands-on how-to videos, visual breakdowns, and practical engineering walkthroughs you can actually use. A family that solves together stays together.